I rewrote it as c squared minus b squared raised to the 1/2 power. Put the square root and wrote it as an exponent. So to speed this up, we know we use the power rule. We know we're going to have 1/2 coming down. In the parentheses, we leave it alone because we've done nothing inside just yet. This is chain rule property. But now, I'm going to multiply by the derivative of the inside. And remember that c squared is a constant.
Look at this.
What happens to that value if I take the derivative of a constant? Where's it go to?
0.
Correct. So we'll get 0, right? Minus, what's the derivative of b squared? B's power rule.
2b.
2b. And then I write what?
gb over dt.
That's correct. dv over dt. So I'm not going to simplify this any further. You can go ahead and simplify this. But obviously, 0 minus something can easily just disappear, and you're left with negative dv, negative 2b dv dt. And then you could easily put this term over in front with the 1/2 and then simplify your coefficients. So now you have a rate of change of dA dt with dv dt. Okay, so to summarize in the first 3 problems, we are going to take the derivative of each of these equations with respect to time. But since time is not present in the equations at all as a letter t, we have to take the derivative of each of our variables with respect to time and show that derivative expression in the final product. When I say product, I mean like the result. So dA dt in the first column and dr dt are related rates with respect to time. And so is dv dt and dr dt in column number 2 are related rates with respect to time. That's what's in blue. That's what shows up. So this is now an application of implicit differentiation. So if I were to take a look at this, this is like, for example, if I were to take this cup and pour my drink inside this cup. This cup is empty. Okay, this cup is empty right here. And I pour my drink in here, and all of a sudden now I have fluid filling up the cup. This fluid is filling up the cup. That means both my height, for example, and my volume is changing at the time. Okay, so that's an example of related rates. 2 things are happening. Both the height of this drink was rising, but the volume was also rising as well, filling up. So now I have 2 things that are happening at once, and time is going on, right? 1 second, 2 seconds, 3 seconds, 4, and so on. So I see that related rate, 2 things are happening. So this was an example of changing height with changing volume. And most cups, as you notice, they're kind of skinny at the smaller radius at the bottom, but get wider at the top. But guess what? My radius is also changing as I fill this cup up. So in actuality, I have 3 things that are happening: height, radius, and volume, all changing in time. So the derivative of number 4 is 1 dv dt equal to pi r squared. Now this is considered a constant from the earlier setup or initial condition. So I treat that as a coefficient. Constants, remember them as coefficients if they're being multiplied to a variable. Then the derivative of h is just 1 dh dt. Now I haven't said anything about the 1 coefficient afterwards. I just want you to see that the derivative of the single variable with no exponents becomes 1. Just like the derivative of x, you get 1. Later on, we'll safely assume, okay, I don't have to write that 1 anymore. I just want you to practice writing that so you don't confuse that. What do I do with the derivative of g or h without a square or a c1? Okay, so 5. I'm going to take a derivative of cosine theta equals to x over 15. Let's take a look at the left side first. What's the derivative of cosine of theta?
Negative sine theta.
Correct. Right. Everyone got that part down. Correct. So I'm going to go ahead and write that down. Negative sine theta. But what am I missing after that now?
The d over.
Right. D over dt. But what am I going to write?
Cosine theta.
Okay. That's what most people would think. And they're probably confused about it too. It's not going to be the cosine theta, it will be theta. This guy goes here. Because that's the part that's actually changing. You already took the derivative of cosine because negative sine. But the actual function within sine, or cosine in this case, theta, is actually changing for time, right? Because if I were to show that this guy was increasing in angle size, it would be the change of this angle, theta prime. So that angle would be opening up, 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 up. So you're looking at that. Okay? Equal to, okay, I have x divided by 15. What is my coefficient here?
Would it be the 15?
That's right. So since it's on the bottom, it's written as what? 1/15. Times, in parentheses, what is the derivative of x with respect to time?
Are you talking about the dx?
Yeah.
Oh, okay, so it would just be 1 or the
One what? 1 times.
times dx over dt.
That's right. Now, I'm not going to simplify this because obviously you guys know what to do here. You do 1/15 times 1 times this. And just find a way to do it. Okay? So right now we're just sticking with this. Writing out the related rates and then simplifying just a little bit to just clean it up in its formality. Okay, now we have the very last problem for today. Now they don't tell you that r squared is a constant. R squared is now a variable. So I have 3 variables, volume, r, and h. 3 things are changing. So if I were to look at question 4, I can just easily write the left side down because it's the same thing, right? 1 dv over dt. We know that. We've already did that part. But now the volume of a cone says I have 1/3 times pi r squared h. So remember that 1/3 pi is a constant, doesn't change, so I'm just going to keep it there. But this time, r and h are changing variables. What rule must I use to take the derivative of r squared times h?
Product rule?
Correct.
Product.
Product rule. Product. So now we know we're going to have a sort of a lengthy expression for the derivative. So let's choose r to be f, and we're going to choose h to be g, and we're going to follow it as f g prime plus f prime g. So if I leave r squared alone, I just have r squared. Well, what's the derivative of h going to be?
1.
1, then what?
dh over dt.
dh over dt.
Exactly. Don't forget that, guys. dh over dt. Because h is not t, so we have to show that h is going to be changing in time. So you took the derivative of h, that's 1, correct. But you don't forget this part, that part right there. Don't forget this part. Now that we took the derivative of h, now we have to go and do the derivative of r squared. What's the derivative of r squared going to be?
2r.
2r, correct. Then what?
And
dr
dr over
over dt.
dt.
That's right. Are you guys getting that hint so far? It's like the 6th time we're doing this. Is this making sense? Time, we leave h alone. Right. We don't do anything with h because they're derivative. So notice here, you didn't tell me 1 dr dt, you just told me that's it. Right, exactly. That's what you have. And so from here, I can distribute the 1/3 and the 1/3 pi inside. I can try to combine my terms as much as I can or simplify it, and that's my expression. So what this reads is the rate of change of the volume with respect to time is equal to 1/3 pi times r squared times the rate of change of the height plus 2r times the rate of change of the radius times the height. Rewind everything here in questions 4, 5, and 6, typically 1, 2, and 3. We are taking derivative of these functions with respect to time, and we're carefully underlining which of our variables are. And that's where we write in blue the derivative change that's next to it. And at this point, so far, what we hold constant, we make sure if it's a coefficient multiplied to the variable, we call it a constant coefficient. If it's not a coefficient, then we keep the derivative of that function with respect to time using the rules that we need. Looking at cosine of theta, just to reiterate again, the cosine of the angle is a chain rule. So we took the derivative of cosine and we got negative sign. But inside, theta is actually changing. Because if I take this triangle and I try to make it open up, make it a bigger triangle, then the angle has to change. So if the angle is changing, so we need to show how much is it changing in time. And so since this is changing, this 15 is fixed, then I know that x and y are going to be changing to some fashion. Okay? So here, you know that the angle and the length of one of the legs is changing in time.